Good afternoon, everyone. Welcome to Google Cloud Next 2017. My name is Dominic Preuss, and I'm here with Robert Kubis from our developer advocate team. And we're going to spend some time talking about Cloud Spanner. So what are the goals of this session? First of all, we want to take you through a brief history of Spanner and why Spanner exists. Then we're going to give you an explanation of what Spanner is today and what is available to you in the public beta. And then any good session has a demo, and Robert will be taking you through a demo. The goal is to talk for about 30 minutes, do a 10-minute demo, and then hopefully have 20 minutes for people to ask questions at the end. So hold your questions at the end, and then please come up to the mic and ask your question so we can make sure that we get your question on the recording. So why does Spanner exist? Let's go back to 2005. Every dollar that Google generated from its advertising system AdWords was on the back of a manually sharded MySQL database. That database was sharded according to customer IDs, and occasionally we'd have to reshard the database. We did a reshard, and that reshard actually took multiple years to complete. It was at that point we decided that there's probably a better way. So we started development of Spanner. So as we were looking at the requirements for the AdWords system, what were the things that Google needed? Google needed a horizontally scalable database. We had lots of customers. We were growing quickly. We had gone from a $10 million a year business to over a $1 billion a year business, and we needed to support that scale. So we needed the horizontal scalability. The second thing is we were dealing with people's money. We had budgets, we had customers, we had partners, we had agencies. We had to have ACID transactions with global consistency. We couldn't accept eventual consistency or any loss of data. So we had to make sure that it was always consistent and we always had ACID transactions. The third thing was every minute that the AdWords system was down for maintenance was millions of dollars of revenue for Google. And so we had to have a system that made sure that we didn't have any downtime. So these are the requirements. And if you look at this today, prior to Cloud Spanner entering the market, there was no good solution that met all of these requirements. And that brings us to Cloud Spanner.
Demo one.
We demand a lot of our databases, and our databases demand a lot of us. They're fragile, expensive, and tough to maintain. When things break, it can be hard to put the pieces back together at the speed of your business, and you often lose data in the process. We've all come to expect that distributed databases can't be globally consistent and scalable. But what if you didn't have to make trade-offs? What if you could have a fully managed database service that's consistent, scales horizontally across data centers, and speaks SQL? This is Cloud Spanner, a mission-critical relational database service built from the ground up and battle-tested at Google for strong consistency and high availability at global scale. At Google, we use Spanner for services that billions of people access every day. It's the only cloud service designed to be a massively distributed relational database with transactions and SQL semantics. And we're talking massive. Spanner can scale up to millions of machines across hundreds of data centers and trillions of database rows, stretching across the globe while behaving like it's all in one place, where you want it. We've built Cloud Spanner to be fully managed and secure. Automatic sharding and synchronous replication with low latency and schema updates without downtime means your data is highly available and reliable. Instead of endless provisioning and worrying about maintenance, you can focus on growing your business. No matter your needs, you don't have to hit a wall with your database service. Get started with Cloud Spanner and build what's next.
Great. So that is our quick introduction into what is Cloud Spanner. So Cloud Spanner is Google's mission-critical, scalable relational database service. So almost 10 years after the internal Spanner project went into production inside Google, we've been able to bring that same level of performance and consistency and scalability to our Google Cloud Platform customers. So what does that really mean? So first of all, Cloud Spanner is a fully managed database service. So what that means is you don't have to worry about upgrades. You don't have to worry about security patches. You don't have to worry about adding storage to your storage array for the next set of data that's going to come into your database system. All of that is handled for you by our site reliability engineering team, who's making sure 24/7 that that service is up and running and that we're meeting your needs. Now, we get fairly pedantic inside of Google around consistency. And so when we say ACID transactions and we mean global consistency, we mean external serializability. So it's the highest standard of consistency. There's a lot of back and forth in the industry about what is eventual consistency or what is global consistency, and we take a very high bar on this, and Spanner meets that need. So this means that you have ACID transactions across many rows. You have relational semantics. So if you're coming off of a manually sharded MySQL database or a Postgres cluster or some other SQL solution, everything looks familiar. So your schemas are defined in DDLs, so standard SQL with SQL data types. You are able to do queries based on your joins and everything you're used to having in SQL. In fact, Cloud Spanner uses the same SQL dialect as what we've rolled out in BigQuery, which is based on ANSI SQL 2011 with some extensions for the additional features that Google offers. So it is standard SQL, and it's the same SQL that you get across the Google Cloud Platform on our data warehousing product, BigQuery. It's automatic synchronous replication. So today, in the beta, we've rolled out regional versions of Cloud Spanner. So what that means is we have multiple replicas across multiple zones inside of a single region. And this gives you 4 nines of availability. It also means that when you write data into Spanner, into Cloud Spanner, you know that it has been written. If we've given you an acknowledgement that that transaction has committed, then you know that that data is there, and any reads that you do after that timestamp will include that data. We give these guarantees so that you always know that you're getting the most consistent view of your data at all times, or a consistent view of your data at all times. Later in the year, we'll be rolling out multi-regional. So multi-regional means that you can actually span your database across multiple Google Cloud Platform regions to achieve an even higher level of availability. So multi-regional Cloud Spanner instances will offer 5 nines of availability. So what that means is you're talking about 2 seconds a month of downtime with 5 nines. And this has been battle tested. And the reason that I can get up on stage and make these types of claims is because we know that we've done this internally. So we've been doing this at Google for almost 10 years with the internal Spanner system. And so we know that when we make these guarantees of availability and consistency and durability, we can stand behind them because we have almost 10 years of battle-tested experience running it internally. Google Cloud Spanner has been used internally for many of our mission-critical applications. So we've talked about Google AdWords, the Google Play Store, and in fact, Google Cloud Platform itself is built on top of Cloud Spanner. So the control plane that manages all of the VMs and all of the services across Google Cloud Platform is actually based on Spanner. So you can have confidence that when you put your data and build your applications on top of Cloud Spanner, you're getting the best of what Google has to offer. So Dominic, you just said a bunch of words. What does that mean? How does that compare to other solutions? So if you compare it to a traditional relational database, so a traditional RDBMS, we have strong schemas, we have SQL schemas and querying, we have strong consistency, we have high availability. Quite often I get asked, how does Cloud Spanner compare to the RDBMS that I'm using either on-premise or in another public cloud? And invariably, they're trying to compare a single node solution to Spanner, which is a distributed system. So when you have a single node master-slave configuration, you're dependent on the master node. That means that you can only do as many writes as you can put through the master node. And if the master node needs to be updated, either get a new version of the software, get a security patch, need to do any maintenance, you either have to take the master node down and take down the whole system, or fail over your master node to your slave so you can do maintenance on the master. What this means is that your application will incur downtime. Now that downtime might be scheduled, but it's still downtime. For Google, it doesn't matter. We're selling ads around the world. We can't schedule downtime. We're making money, and we have a system that is reliant on the system 24/7. So we can't have downtime, either scheduled or unscheduled. So Cloud Spanner, because of its distributed nature, means that we can do updates, security updates, any maintenance that we need to do on the system by moving your data around on the multiple nodes, and you don't see any downtime. In fact, you see nothing on the performance side of what you experience. You'll see a consistent experience even when we're doing things like upgrades and security patches. So in that sense, it's horizontally scalable. So the way that you achieve additional scale is you add nodes, which is what you would normally see in a NoSQL database, which we'll talk about in a second. So instead of relying on vertical scalability, which means that if I need more throughput through my master slave, I just put it on a bigger box. I give it more RAM. I give it more memory. And so that's a vertical scaling strategy. And so with Spanner, we give you horizontal scalability. So you don't worry about, I'm on the biggest VM. I really hope this provider makes a bigger VM because I'm going to run out of size soon, right? You know that we can always add additional capacity so that you can grow your application. Also replication. So traditional RDBMSs, one of the ways that you can scale out horizontally is you can shard your read and write workloads. So you can add additional read replicas to your system, and then you can do your reads off of those read replicas, therefore giving additional write capacity to your master node. Now the problem there is that those reads of the read replicas are stale. There is a replication lag for the data that's making that read replica. And so it's up to you and your application to know that you may or may not have the most consistent version of the data. If you need a consistent read, you have to go back to the master node, and therefore using up some of those resources and take away some of your scalability. So that's how it relates to a traditional RDBMS. How does it relate to NoSQL? So the pattern that we would see over and over and over again with our customers is, both our enterprise and our startups and smaller companies, is that they would build an application using a traditional RDBMS. Might be MySQL, might be Postgres, might be name your commercial database. And then what happens is they just grew. And we all know that data is growing exponentially. It is growing faster at a faster rate than it's ever grown in our history. And so the requirements that we have in our databases continues to grow. And so often what happens is a company or project has this relational database that backs their application, and they hit the upper bound of what they can do for scale. So their only immutable requirement is horizontal scalability. So they then go and choose a NoSQL solution, Cassandra, MongoDB, whatever happens to be, and they basically trade global consistency for horizontal scalability because that is their immutable requirement. And then they write a bunch of application logic or use other tools to try to get around the transactional semantics of having consistency only at a shard level or not across the entire database. So what Spanner allows you to do is to not have to make this trade-off. Now, if you've outgrown your RDBMS, Cloud Spanner is not a drop-in replacement. It's not a MySQL compatible database. It's not a Postgres compatible database. So there is going to be work for you required to migrate your traditional RDBMS application onto Cloud Spanner. But you get to know that when you make that transition, you don't have to make a trade-off between horizontal scalability and global consistency. I'm often asked, what was the hardest thing about taking the internal Spanner application and exposing it to our Google Cloud Platform customers? And the answer is making it open. So Google is committed to being the open cloud. And so we've done everything we can to adopt open standards and existing protocols and APIs that exist in the outside world. We aren't trying to move everyone on the Google proprietary technology. We're trying to move and solve customers' needs where they are by supporting those standards. And so Cloud Spanner spent a tremendous amount of time to make sure that this was true. So we started with standard SQL. We've had a number of different SQL dialects across the Google Cloud Platform. And so we decided that we needed to come to a standard SQL dialect across all Google products. So we took ANSI SQL 2011 as a spec and then extended that. And so what this means is when you look at SQL in Spanner, you see normal SQL data types and the types of queries and joins and things that you would expect. So we make it as easy as possible for customers by reducing the friction and the impedance mismatch between their existing solution. The second thing is we spent a lot of time on enterprise requirements. Cloud Spanner actually launched with the best integration across all of our various cross-platform initiatives for identity and access management, encryption, and audit logging. It came out of the gates in beta with all of the features that a traditional enterprise that has high security needs would need to be able to adopt this product. And so we spent a lot of time investing in that and making sure that the product had those features from the very beginning. We also spend a lot of time in client libraries. So we like to talk about being a very developer-friendly platform. And being developer-friendly means two things. It means that you've got great documents and great documentation, and you have really strong client libraries. So we spent a ton of time working with our early access customers. Cloud Spanner was in early access for over 12 months. And what we were doing during that time was onboarding customers, showing the documents, finding the holes in the places that we forgot to document things, adding those documents, and really doing lots of iterations on the documentation so that when we launched, we actually had all of that ready for our developers. The second thing that was really important was our client libraries. So we spent a ton of time on our Java, Python, Go, and Node.js client libraries to make sure that they were fully baked, they were optimized for performance. We obscured any of the common gotchas that you would have if you were trying to use the API directly in an idiomatic way for the language. So we spent a ton of time working with the various teams to make sure that we had a first-class developer client library in these languages. The last thing is JDBC. So in case you haven't heard this yet, the partner ecosystem is incredibly important to Google. And so one of the things that we did to make it as easy as possible for both customers to adopt and partners is that we launched with a JDBC driver. That JDBC driver is read-only, and what that means is that we can hand that to a number of our partners or your internal customers, and they have a fully understood client library that they can often plug in with very little work to their frameworks. And this allowed us to launch integrations with a number of partners early because we were able to deliver them a JDBC driver, and that was able to decrease the time necessary for them to implement access into Cloud Spanner. So what types of workloads are appropriate for Cloud Spanner? So as we were going through the early access program, we saw a number of patterns emerge from the types of use cases that people found for Cloud Spanner. So the first one was transactional. If you have an application that requires transactional consistency or complex transactions, then that is an ideal use case for Spanner. So if you're dealing with things like inventory management, where you can't sell more products than you have, or if you are trying to manage financial transactions, you have to make sure that you always have the right amounts, and you have to have really strong transactional semantics to be able to support that. So what we saw is a number of the companies that we have worked with had a manually sharded system or had built a transactional system on top of their manually sharded or eventually consistent data store to make sure that they were guaranteeing transactional consistency. So what Spanner allows you to do is to push all of the transactional code and all of the responsibilities for maintaining transactional consistency into the database. So what this means is that you have much simpler architectures, much higher velocity for your developers, less code that can go wrong and introduce bugs, because you can rely on the database itself for maintaining and providing all of your transactional consistency. The second one was scale out. And people often assume that unless they have tons of data, they can't use Spanner. And the answer is, if you have a mission-critical system that requires high availability, then Spanner can be a great fit for you. If you have 10 gigabytes of data or you have a petabyte of data, it doesn't matter. You have a mission-critical application. And so Cloud Spanner gives you a cloud-native mission-critical database that also provides scale. So if you have hit the upper bounds of what you can do, and we continue to see other cloud providers and database providers rolling out kind of incremental changes in the amount of data that they can store, what Spanner does is allows you to have a non-incremental change. We go from being able to store specific single-digit terabytes of data into as much data as you have. So if you happen to have a very large customer set, or large number of transactions, or a lot of data that you have to have transactional consistency, then Spanner allows you to meet that need without having to take any trade-offs. Another common use case is global data plane. And this is very common inside of Google and actually the Google Cloud Platform use case. So if you have, let's say that you have user bases that are around the world. You have a set of users in North America, a set of users in Europe, and a set of users in Asia. And you want to keep all of the user data close to the customers, then you can do that. You could have a regional instance or an RDBMS in the US, one in Europe, and one in Asia. But what you need to know is have a single global system that tells you where that data lives. So for this user ABC, I know that that user is homed in Europe, so I'm going to go to the European instance to go ahead and get that data. And so this global control plane, where it might be a very small amount of data, but you have to be able to query it from everywhere, have low latency, and know that you have a consistent view of the data, is another very common use case we saw both inside of Google and we're starting to see more commonly in the outside world. The last one is database consolidation. Everyone knows the story, right? You keep your user data in MySQL or Postgres, you keep all of your event and logs data in a Cassandra cluster or in BigQuery, and then you ETL the data around, right? Every night you copy a copy of your user table into BigQuery so you can do joins against it. What we've seen with Cloud Spanner is it allows you to consolidate your databases into a single source of truth. So you could take your user database that might be in Postgres or in MySQL, and you can merge it with all the events data that you have in Cassandra or MongoDB or BigQuery, and you can combine them into a single database. You no longer have to ETL data around. You don't have to worry about staleness of data. You can do joins across all the data, and you know that you have a single, consistent source of truth for all of your data. Again, it is a tremendous gain in productivity for your development teams if they don't have to worry about multiple data stores. If you can put all of your data in one place, and Cloud Spanner makes sense for that, it removes tremendous complexity from your stack. So that removes bugs, it makes it easier to maintain code, it increases developer velocity, and this is, again, something we've seen a lot inside of Google, and we're starting to see with our Google Cloud Platform customers. So how does Spanner do this? I say that it's horizontally scalable, so what does that mean? So for Cloud Spanner, you start with a Cloud Spanner instance. And Robert is going to demo how to actually create one of these, and you can see how easy it is. But you create a Cloud Spanner instance. And when you create that instance, you basically tell us what you want your replication topology to look like. So if you're using a regional Spanner instance, we have multiple replicas in multiple zones inside of a single region. And then each of those replicas has its own set of compute resources and storage. And then you put your database inside of that instance. So an instance can have 100 databases, and then each database can have 2,000 tables, and each of those tables can have as many rows as you want. And so what this means is that your data is actually replicated across each of the replicas, and we've got full copies of all the data in all the places. And so there is multiple replicas running at any given time. So what happens is if somebody comes in and wants to make an update, so let's say that you want to update a row in a database, or let's say you want to update 100 rows. That update comes into the system and goes into one of the replicas. This is where Spanner magic starts to happen. That update comes into the system. We know that each of the different replicas has parts, they have all the data, but we know that certain parts of the data are owned by different nodes. So when that update comes in, we come in and we notify the appropriate nodes, and then that data gets replicated across all of the replicas. We use a custom Paxos algorithm that allows us to do consensus-based writes on the system, and this is what allows us to have our global consistency. So we have a custom Paxos algorithm, and we have two-phase commits, which allows us to have global consistency across the database at all times. We try to do everything without the two-phase commit, but if you actually are if you're trying to update data across multiple nodes, then we fall back to a two-phase commit to make sure that we don't lose consistency of the database. So this is all well and good, and Spanner sounds magic, but there has to be some differences. They can't just be a drop-in replacement. And the answer is you're right. So to get the advantages of a distributed system, we impose certain design constraints, or we impose certain concepts. So the first one is the way that we lay out the data. So in a regular relational database, if you had two sets of data that were related, you would have two tables, and you may or may not have a foreign key constraint, which would allow, if you delete one row, then it deletes all of the children rows. And so this is the way you would lay it out in a normal relational database. PostgreSQL does support child tables, which implement some of this, but it's for different reasons. So what we've done in Spanner to make it performant and to help customers tell us what data should be grouped together, we have the concept of interleave tables. So what this means is that when you have tables that are dependent on each other, you literally interleave them together into the same table. So you can see our top level row is the Beatles, where the artist ID is number 1. And then we have albums that are under it that are from the artist, and they have IDs 1 and 2. So we have the primary key for Beatles, which is 1, and then 1 and 2, which are the primary keys for the child table. What this tells us is that all of the information that is under Beatles is related. And so what that allows us to do is to group all of the data together on a single node. So if you commonly are doing queries where you say, show me all of the songs for the Beatles, or show me all the albums for the Beatles, and you know that your queries are going to be within a subset of the data, by using interleave tables, you can tell us the logical grouping of your data. And this allows us to do a better job of splitting the data across multiple nodes, which allows us to respond to queries more quickly because we don't have to rely on two-phase commit. We can serve all of the data off of that one section of the data in a very quick way. So what does this look like from a schema point of view? So when you define your schema, as we talked about, we use DDLs, standard SQL, create table singers, singer ID is int64, not null. Singer name is a string, max length, and primary key is singer ID. So we need this primary key to know how to split your data up and shard your data across nodes. So then if albums is a subset of all this data and is dependent on the parent table, then we can say create table albums, singer ID int64. So child tables have to have all of the primary keys of its parent. So it has to have singer ID. And then we've added album ID as a second primary key. And we also have album name, which is a string. And then when we define the table, we say interleave in singers. And so this is the concept of foreign key constraints that Spanner supports. It's not arbitrary foreign key constraints because that doesn't work on a distributed system. By telling us how to group all the data together, then you can start to do things like cascade on delete and some of the other benefits that you get from a foreign key constraint. But we only do this at a interleave table basis. The other thing that's great that I love telling customers about is schema migrations. So the other thing that this allows us to do is no downtime schema migrations. So you can actually alter your table and add a column, in this case age. We can apply that to the database, and that updates the schema on the fly. So no downtime online, and you know that once that transaction, the schema update is done as a transaction, once that commits, you know that all subsequent reads after that transaction have the new data. Again, getting back to the problem we talked about with AdWords, we couldn't handle either locking the database or shutting down the database to do schema migrations. We needed to be able to do schema migrations on the fly. So alterations to the schema are online. So what does this look like in code? So in any of these sessions, we try to give you actionable information. I'm a Python guy, so I've gone ahead and pulled the Python code. So if you use our Google Cloud client libraries, so we've rolled open source client libraries in all the primary languages. So if I install the Python Google Cloud library into pip, so pip install Google-Cloud, I can then import Spanner from Google Cloud. I instantiate a client, so that client allows me to talk to the service. I then say, I need my instance, so please give me my instance ID. And then from the instance, I can grab my database. So I say, what is my database ID? And then I ask my instance for the database. I now have a handle to my database where I can start to send queries. So I could do result sets by saying database.execute SQL and pass it SQL queries. And so these 10 lines of code are all that is necessary to be able to be up and running with your Cloud Spanner instance. We really tried to make it as easy as possible. There's lots of intermediate steps that are happening here that we've been able to obscure by having really strong client libraries that do a lot of the heavy lifting underneath the hood for you. Things like connection pooling and things that could be gotchas if you aren't familiar with how to use the service. So right before we get into the demo, how does this fit into the broader schema? So Cloud Spanner sounds fantastic. Is that the solution for everything? And the answer is no. Cloud Spanner is one of a portfolio of solutions that allow you to build your applications on top of Google Cloud Platform. So starting with Cloud SQL, so if you have a framework, whether it be Django or WordPress or Drupal that requires MySQL, then you can use Cloud SQL to manage that MySQL instance for you. So it's a traditional RDBMS that's being managed for you by Google. If you have a document database workload, commonly in mobile and web, then Cloud Data Store provides you that document database. Fully scalable, it's shared resources, so you can literally start from $0 a month all the way up to SnapScale, who just went public. So you can scale all the way up on Cloud Data Store if your data is non-relational and fits into a document database workload. Cloud Bigtable is our analytics database. So this allows you to do low latency, single millisecond reads and writes, and really fast table scans for your IoT, time series, ad tech data, MarTech data. It's a fantastic solution for that. And then BigQuery is our data warehouse that allows you to write all your data in, mostly append some mutations so you can update and clean up your data. But it's really our data warehouse. So what Cloud Spanner does in the portfolio is gives you a place that if you've gone to MySQL and Cloud SQL and you're using that as your solution, if you need to be able to scale past it, you know that Google provides you an option. So it really gives you a future-proof path to be able to move from your existing application on either MySQL or Postgres or whatever you happen to be using and continue to grow out as a scale-out relational database. And with that, I'm going to bring up Robert to get started on the demo. One of the questions that I just went through, I used a lot of words. Flowcharts are usually helpful. So what we did here is we put together a decision tree that allows you to decide which database service you would use for which offering. So first of all, is your data structured or unstructured? If your data is unstructured, you're going to put it into Google Cloud Storage. That way you can use it and access it there. If you need mobile SDKs, then Firebase Storage will provide you a mobile SDK onto Google Cloud Storage. If your data is structured, then the question is your data analytics? Do you have an analytics workload? In which case, you'll come over into the analytics branch. If you need low latency and lots of mutations, use Cloud Bigtable. If you don't, use Cloud BigQuery. Coming back down the middle, if your data is relational, and the answer is no, then you have Cloud Data Store. And if you have mobile applications, you have Firebase real-time database that provides you mobile SDKs for iOS, Java, and the mobile applications. If your data is relational, then the question is, do you need horizontal scalability? If you don't need horizontal scalability, then Cloud SQL is a great solution for you, and it's going to be your easiest path to building an application. If you do need horizontal scalability, Cloud Spanner is there to meet your needs. So this is a quick way for you to kind of navigate which of the various database technologies will serve the need for your application. And lastly, before we get to the demo, as I said before, partner integration is very important to us. It's why we spent a lot of time on the JDBC driver. So we're very excited to have Xplenty, Zoom Data, Looker, and MicroStrategy and iCharts. They all are in the process of launching or have already launched support for Cloud Spanner. So some of your favorite BI tools are already integrated. And we're working with Informatica, Illuma, and Tableau. They've started work, and they'll be rolling out their solutions later in the year. So again, if you are already using Tableau or Looker or one of these solutions in your stack, we're going to make sure that we're integrated from the very beginning to make it as easy as possible to migrate data in and out of Cloud Spanner. So with that, I give it to Robert.
All right, thank you, Dominic. Hello, everyone. So Dominic presented you a lot of features and arguments why to use Spanner. So I want to show you how you can get started today with it. So your first stop should be cloud.google.com/Spanner, where you find a wealth of information about our Spanner product. You find white papers, best practices. You find Eric Brewer's recap on the CAP theorem and Spanner. So there you also find your developer docs. And I want to stop here and ask a question. How many of you are developers here in the room? Awesome. So you're the right audience for me. So as Dominic mentioned, we have a couple of client libraries: Go, Java, Node.js, and Python. I'm going to concentrate on Go if I get to it today. So to get started with an instance, you go to the Google Cloud Console. So console.cloud.google.com. Make sure that you're logged in. And then we have on the left side a nice drawer here where you can type in spanner. And you find it, and you can go there. So to create an instance, you click on instance, you choose a name. It's awesome spanner, for instance. And then I select a regional configuration. Now we have as Dominic mentioned, the multi-regional is coming up later this year. Right now you can choose between 3 regions: Asia, Europe, and US. I'm going to choose Europe. I'm personally from Europe, so I prefer Europe. I want to have my spanner instance to give me all the answers, so I select 42 nodes. And we create, and as you can see, with a snap of the finger, you have your instance with 42 nodes. So now we can get started and create a database. So here I choose and say, okay, I create a demo database, and I create a schema. So I select the table. You can all do this also from the command line with gcloud SDK. So download the gcloud SDK, and then you can do all this on the command line as well. So for instance, we have the singer, we had an ID, an int, perfect, and then we say a name, which is a string here. Okay, done. And then you select your primary key, you add the table, and now you have your first table. Now we can add another table, and as we mentioned before, I think we had albums here. We can now interleave this as well. So I want to, for instance, interleave or not. So I can go through all this and create this. Let me choose this. So I want to interleave the table with my single table. I want to delete on cascade delete. So I get already the ID as my primary key from the album. And then, for instance, I say it's like an album name here. All right, and again, a string. We are done. We will have to choose a primary key as well, and then we add the table here. Say album name. Okay. Cool, and we create. So that's basically done in the background. As we mentioned before, we have online updates. You can see already it's done. Cool. Now I want to switch to a different instance where I have some preloaded data. So in this preloaded data, I have a scenario where I have think of Ticketmaster or something where you can buy tickets. And to explain that to you a little bit, I have a crappy schema here. Sorry about my drawing skills. So what I'm going to show you here, I want to show you some best practices, how we came up with the schema and what you have to pay attention to if you want to scale horizontally with your database. So here we have a multi-event. Think of a tour, for instance, a Coldplay tour, which is in many, many countries. So the Coldplay tour would be a multi-event. Each of the concerts in each country is an event. Then we have different venues which have different seating configuration. Think of like a stadium which can have sports events or a concert. And then we have a ticket category which basically attaches a price to a ticket for a certain event. So at the Coldplay concert in a stadium, we have a certain ticket price for each seat. And then you see on the right upper corner an account. So that would basically somebody who comes to our website and signs up and wants to buy a ticket, that would be representing that account. So now I have this table preloaded here. And what you can also see here in the console is you have a multitude of things that you can check into. So we see already here my database is mere 7 gigabytes big. I can go to the monitor tab where I see things like how many nodes do I have, how much CPU utilization do I have, and we recommend not to go over 75%. So if you see that you're approaching this utilization, you can easily add nodes. You see operations and throughputs and things like that. So this little spike that you see here was me loading the database. Okay, so I want to show you an example query that I have here. which is based on the schema that I just showed you. So the capability that you have as well, here in the console, you can directly run your queries out of the console. So I'm gonna run this query. It should be rather quick. What does this query do? It basically gives you back the events for the next week, where we still have a lot of seats available for this event. So you see here we have a couple of events with 10,000 available seats, and then the seats availability, basically how many tickets didn't we have not sold so far. So this is, for instance, a query that you could use to promote events that are not going well in terms of selling your tickets. Now we see, if I go to the explanation tab, you get a query explain. And you can see like what is this query doing? Like I see here a couple of table scans that I'm doing, distributed unions and things like that. And I looked at this query before and I saw like, okay, this is not performing optimal. So what can I do if a query is not performing optimal? And as like with any like bigger database, relational database that you have out there, you have the possibility to give the optimizer some hints. And that's exactly what I'm going to do here. So it was mentioned by Dominic that we have the ANSI 2011 SQL standard with extensions. And one of these extensions is that I can force an index, for instance. So I have an index defined on my seeding category, and I say add, and then the places, and say force index seeding category by ID. And then I run this whole query again. And if you have paid attention, you saw this query ran before in 750 milliseconds. So fingers crossed, this is better now. You see here, I did an optimizer hint, and now my query runs 3 times faster and scans a lot less rows. All right, so another thing what we have, all of the cloud products, they are integrated with the products that we have. So one of the products, for instance, for monitoring is our Stackdriver solution. So in Stackdriver, what you can do is you can monitor your Cloud Spanner instance. And I have here a pre-created dashboard, and I want to add some more things. So right now I have nodes and storage, which I'm monitoring. If you want to add more things, you basically can select from the add charts. You can have here a resource type Cloud Spanner, and then you can select the metric that you want to select. So for instance, I want to check the CPU utilization. So util. Okay, and then you can select and say, okay, I only want to have that monitoring one of my databases. And the nice thing of this is you can also set up alerts with this. So if your Spanner instance is approaching like a certain grade of utilization or storage, then you can get alerts to your phone and can easily increase the node count. So node count, adding or taking nodes away if you want to save money or you like utilization is low, you can all the time go to your instance, edit nodes, and for instance go from 8 to 5, and then say save, and then we will reduce the nodes. So it's a fully managed solution where it's very easily to set it up, get started, load data, scale in and scale out as you wish. So how are we doing in time? Okay, so one more thing. Dominic mentioned he is a Python guy. I'm a Go guy. So I'm usually doing Go. So how does it look in Go? It's very easy as well. So what you do is basically you have the database path where you load or where you take the instance or the project, the instance, and the database that you want to talk to. You set up a client. We have that here. And then you can basically run your queries. So what I'm doing here is a very simple query. I want to have all the multi-events that are happening for today. And because I don't care if like I'm a little bit like out of date with this, I actually can define time bounds for this query. So I can actually say to Spanner and say like, hey, I don't want to have a strong consistent read in this case because I don't think that we update the multi-events so often. So I'm okay if I have a little bit of staleness. And in this case, what you see here, I'm saying like I'm okay with 15 seconds of staleness. And that allows you, for instance, in a multi-regional setup to read from a local copy in a different region, even so if there's not the primary copy of it. All right, so with that, I want to lead into Q&A, and I want to ask Dominic to come back on stage, and we are here for you to answer any questions.
And so we're going to do, we've got about 15 minutes for Q&A. So if you have questions, please come up to the mic. Last thing is I want to put a quick plug in for some of our other sessions. So if you're interested in Spanner and databases in general, we have the Spanner 201 session tomorrow. We have a great session on optimizing Cloud SQL performance. A good class, again, on talking about other storage solutions. So I didn't spend time on Google Cloud Storage or some of the other ones. And also Zero to App, live coding an app with Firebase and GCP, which is one of my favorite sessions that I've seen. So with that, we'll open it up to questions.
So we have 2 mics over on the left and here on the right.
There's a room full of developers. I know someone's going to ask a question.
Okay, I have one question, just kind of a broad question. So you said that Spanner is not for every use case. It's more for transactional applications. But you also said that Spanner is underlying all of Google's services and products in the cloud and their internal services and infrastructure. So what, if anything, at Google is not running on top of Spanner? And in other words, like if you remove that system, if you remove the atomic clocks from the infrastructure, or say the satellites fell out of the sky and you couldn't get the timing, would all just Google just come to a grinding halt? So how does that component fit in with, as opposed to like, I know there's like CockroachDB that's got a similar kind of approach going on, but they're not using the same infrastructure that you guys are. So I was just wondering how the actual infrastructure and timing from the satellites and atomic clocks fits into that.
All right, there's about 3 questions in there, so let me try to unpack it. So first of all, we have a number of use cases internally for various databases. So most applications inside of Google will break up into one of 3 use cases. It's Bigtable, if you've got a wide column scenario where you need single millisecond reads and writes. So this is things like metrics data, time series data, IoT data, event-driven data. That's really where we use Bigtable a lot internally. You don't need Spanner. You don't need global consistency on the writes. You single row atomic transactions is sufficient for that use case. So a lot of internal usage on Bigtable. We also have a number of people using MySQL internally. We use it initially for the AdWords system. There's lots of great tooling and frameworks that use MySQL. So if you're building an application where it's about velocity and the ability to work with third-party tools, that's a great solution. Another one that we use internally is obviously BigQuery. Internally, we call it Dremel, but we use columnar storage for those kind of analytics queries. So that's yet another storage system. So we use Spanner internally for anything that is highly available and requires transactional consistency, and the data model is relational. If you have a data model that's really just key value, then you're often going to do better in some of our other solutions. So Spanner really is around those relational, transactional use cases. The second question was around what happens if the satellites fall out of the sky. If the satellites fall out of the sky, the least of your problems is probably Cloud Spanner. But given that, there's a bunch of fallbacks. So if for some reason we no longer have access to the atomic clocks or the GPS, basically the system has fallbacks, and essentially the degraded state for Spanner is just slower. So if there's a failure of any kind and we don't have access to all the normal resources, we'll just fall back to comfortable defaults and the system will slow down, but it'll continue to operate. You know, if we don't have those atomic clocks and we don't have the GPS, then we aren't as sure about the time. We don't have a universal wall clock, so we can just make sure that we have bigger time bounds, so we'll continue to operate. Third question, CockroachDB. So CockroachDB is looking to solve a similar number of problems. If you have questions about CockroachDB, Ben Darnell, the CTO of CockroachDB, is running around somewhere, so you should definitely chat with him. But they're trying to solve the similar use case of Spanner with software only. So they're saying if we could take the software anywhere and run it, wouldn't that be great? And so they're solving the problem without the tight integration between hardware and network. So on Google, the 3 things that really make Spanner possible are our custom Paxos algorithm and 2-phase commits, our integration with hardware, atomic clocks, and high-precision GPS clocks, and then the fact that we own all of the fiber network between our data centers, so we get as close to speed as light as possible on the network. Those 3 things are really what allows Spanner to achieve what it does. Other software-based solutions are going to have different design constraints, are going to come up with different problems because they don't have those dependencies. So slightly different approaches to the same problem, but all things for you to consider as you're looking at different solutions. I think I answered all the questions. Awesome.
So Dominic, we're a global company, and we absolutely must move a relational database to the cloud. We have had some success in vertically scaling this particular database, but we see the writing on the wall. So our latency requirements are pretty tight. So and this is kind of an open-ended, maybe tough question to answer, but have you done any relative measures on latency, just some sort of latency benchmark? Because that's really the key thing for us at this point.
Yep. So quick thing. So if you're moving off of either an on-premise or a legacy application, first question is it a third-party application or did you write it? Right. If it's a third-party application, then obviously they would need to support Cloud Spanner as a backend, and that's a longer conversation. If it's a custom application, then it's an easier conversation. What I would tell you to do is first of all, you should come to the Cloud Spanner 201 session, and Peter from Quizlet will go through their benchmarks. But effectively, what happens is that Cloud Spanner, specifically the regional instances where we have 3 replicas in a single region, you're going to see higher latency at the bottom, right? You're never going to see 1 or 2 millisecond reads. You're going to see 4 or 5 millisecond reads, and you're never going to see single millisecond writes. You're going to see 20 to 30 millisecond writes. So then what happens is, the good news is it never gets worse than that. Right? Because it just continues to be consistent. So as your load increases and you add nodes, you get super consistent performance. So what happens is you don't get the low end of the distribution. We kind of start in the middle, but then we always stay in the middle. And so if your application, if you need sub-single millisecond transactions and reads, then Cloud Spanner is probably not your answer. But if your application can handle single millisecond, where maybe it's 6 milliseconds for a read instead of 2 milliseconds, then you're clearly in an area that Cloud Spanner plays in. And of course, all of this is completely caveated by the fact that it depends on the shape of your data, your schema, your queries. But in general, if you've optimized everything, you can expect that kind of performance.
Thanks, appreciate it.
So we have some of our Loud developers using stored procedures and all those things in Oracle. And if you have to migrate those things, do you have any migration service, or does it support some kind of stored procedure things?
Yep, so Spanner does not support stored procedures. We don't support user-defined functions. And the reason, again, is that a lot of those don't work well in a distributed system. In terms of migration, we're really engaging really hard with the partner community. So all of the migration tools that you use today, we're working to get support for Cloud Spanner and all of the database services to make it as easy as possible. So we don't provide any Google-specific migration tools, but we are working with companies like Attunity and Informatica to make sure that they have support for Cloud Spanner so that you can build data pipelines and do your migrations. And so all of those things, unfortunately, we've only been beta for 3 weeks, and so we're still rolling out all those partner solutions. But there is not a good solution. So if you, the deeper you go down the RDBMS specific functionality, like the farther you go down the stored procedure route, the further you go down the PLSQL path, the harder it is for you to move to any database, and Spanner isn't any different. So the more RDBMS-specific services you use, the greater the migration is going to be to move to any other RDBMS, and Spanner is no different.
Yeah, hi. So I have a question. So if you make bad database design decisions or you outgrow them, how easy is it to back out of things like interleaving?
So, and again, I'm going to pitch again the Cloud Spanner 201 session. Because you have so few knobs, right? Robert went through the demo. The only knob you have is how many nodes, right? There's no other knobs. And so your application performance is 100% dependent on your schema and your queries. So the good news is there's only so many ways you can shoot yourself in the foot, but there's 2 really big ones, right? And so schema design is incredibly important as you're building the application. This is also true in Cloud Bigtable, right? Schema design in Cloud Bigtable is a similar problem. You really have to do it correctly up front to make sure you have success down the path. The good news is you can do schema migrations with no downtime, right? So you can say, oh, this column's wrong, it's the wrong type. I can't alter the type of the column, but what I can do is create another column that has the right type, move the data over, then delete the other column, and there's no downtime. So the good news is there's no downtime, but making dramatic changes in your schema, and Robert, as we've gone through and built some of these demos, like, oh, that was a bad design decision, got to change the schema, got to reload the data. You really want to make sure you spend time up front to get that right, because while it's not that painful, it's still pretty painful. So you have to be very careful about your schema design up front.
Thanks.
So you already explained about the consistency of the performances. So I'm wondering, when you are reaching to the point of the data, then you mentioned about we can add them more nodes. And is this done automatically, or we actually have to have something notify us, okay, you reach to a certain capacity and you have to add more nodes than to keep the consistency?
Yep. So today, Cloud Spanner does not support auto-scaling, which is as you get more load, we add more nodes. What we recommend today is that because we have Stackdriver integration, you write a cron that every minute or every 5 minutes or every 10 minutes looks at your CPU utilization, and if you need to add more nodes, does that for you. It gives you a little bit more control over cost, because the nodes are going to be the majority of your cost, but it does require some work on your side. You can set up alerts in Stackdriver, right? So you can say, send me an email if my CPU utilization gets above 80%, and then you can just respond by adding more nodes. Adding nodes only takes a few seconds, so within a minute, they'll be serving data, and you pay on a per hour basis. But adding nodes is very fast, and you can actually scale up to additional load very, very quickly.
Okay, sounds great. So another thing is regard to the interleaving data model. I'm just curious, the interleaving data model, do you guys actually create a new, like a table, or just somehow some other magic?
So interleave tables are separate tables that share primary keys. And we co-locate them on the nodes from a data locality point anytime we can, but they are individual tables that can be addressed via SQL. So they are separate tables.
So they are separate.
Yep. Think of them as a child table that inherits from the parent. Yep. And so it's not inheriting columns and rows, but it is a separate table that shares part of the primary keys from its parent.
I see. Got it. Thanks.
Yep.
Hi, two-part question. First is the on-disk format columnar, and the second, and I'm curious because you mentioned potentially using Spanner for some analytic use cases, and I'm wondering where the break-even point is with BigQuery. Second question. Did you consider adapting Bigtable to form Spanner? Because there are examples in the industry of creating SQL on top of a NoSQL database and maybe having synchronous replication and things like that. I'm curious if you didn't, why did that get ruled out?
Yep. So the first answer is we don't really talk about how we store the data format in Spanner. We do store the data files in our distributed file system that we use across Google, but it's something that's evolving and changing, so it's just an implementation detail. It is not columnar, to answer your question. In terms of BigQuery, so Cloud Spanner is an application database that can also do analytics. If all you want to do is analytics, then either Bigtable or BigQuery are going to be a better solution for you. Cloud Spanner does not support a lot of the analytics functions that you would get out of BigQuery. So you don't get auto-partitioning, and you don't get some of the aggregations, and some of the more data warehousing SQL functions. They're not supported in Spanner. So you can use Spanner for analytics, but only if you're already getting a bunch of value from the fact that it's an application database. In very few scenarios where you get enough value out of it as a pure analytics database that it would be better than either Bigtable or BigQuery for your application.
And the second question, why not just adapt Bigtable?
Yeah. So we have a bunch of projects internally that basically, we have replication in Bigtable internally. It's something we're working on for Cloud Bigtable. But that replication is always eventually consistent. It's not designed to be a globally consistent transactional database. And so to get the performance that we needed to get out of Spanner, we had to take a fundamentally different design approach to achieve that. And so Cloud Bigtable, that's not its design. It was not the way it was designed from the beginning. So we had to work off a different design to achieve the global consistency and the latencies that we needed in Cloud Spanner.
Sort of related to the BigQuery questions, if you start doing some of these larger analytics queries, what does the performance of that look like? You sort of said it's anything you do is low performance, or good performance, but I assume that's not true if you start doing much bigger queries. How does that start?
Yeah, and so this is the last question because we're going to run out of time, so I apologize to the people that were waiting. Please come up to me afterwards. I'll be happy to answer your questions. The answer is that if you're doing these really big aggregations that are longer aggregations than they run for multi-seconds or a minute on BigQuery, those are going to time out in Spanner. Right? Like Spanner isn't designed for super long running queries, and so there's a point at which you're going to exceed the time at which you can run some of these queries. And again, major aggregations, or if you're trying to do lots of table scans, that's not Spanner's strength, and that's an area where BigQuery is always going to be a better solution. So anyways, thank you everyone for your time today. I really appreciate it. Thank you to Robert for building the demo.